Ugh. In case any of you couldn't tell, I'm a giant nerd. And if you understand all the references behind the background and the helmet I'm wearing and the music, then you're probably a giant nerd also. Okay. Anyway, to math. What we're going to work on today is another example, how to do this equilibrium analysis. And we're going to be doing something just more complicated simply because there's going to be no numbers. And so we're going to have to deal with parameter values and variables that are just unknown, left as letters and the whatnot for us to figure out. And I want us to be able to work through the challenges that come with this of like keeping everything straight in our heads and really sort of what are the things that I'm thinking about. So what may be useful for you is to watch this once, and every time I bring up something like, so we have to think about this because, make a note like consider blah blah blah, consider blah blah blah. So that way you kind of am able to make for yourself a recipe that makes sense for you for working through these things. Okay, and hopefully we can keep our work relatively organized. Now, what I want to do is an ecological example. And in order to facilitate that, I'm going to say a little narrative, and then we'll see how we express that mathematically. Okay, so the narrative goes as follows. All right, I want two species who occupy a shared area. Okay, the area can support the two species at different levels, and they have their own biology, so they grow at their own particular rates. Now, these species compete over resources and area and the whatnot, and that competition is symmetric, so each feels the effect the same way. Get all that? Okay, so if we looked at the chart of biological interactions, this is a case of antagonism, all right, because it's going to be competition. And let's see how we take all those facts and kind of get them into equation form. Okay, so first things first, let's think about the x species, dx dt. All right, now the area can support them at a particular level. That should tell us that it's not exponential growth. Okay, and in fact, logistic growth is probably the equation that's going to best fit that idea, at least in a simple way. Okay, so we have r times x, that's the intrinsic growth rate, minus or times 1 minus k x over k. I'm incapable of reading, where k is that level of individuals that the area can support. Okay, because if we just look at that equation right there, it's got two fixed points, one at x equals 0 and one at x equals k. The one at x equals 0 is unstable, the one at x equals k is stable, and so it goes up to that value, okay, just in case we couldn't remember logistic growth. Now, before we do interactions, let's go ahead and write down the facts about the second species, all right? So dy dt equals. Now, of important note here is the different animal, so it should have a different growth rate. I'm writing sy. Now, the area can support them, but I said it supports them at its own level, at a different level. So we again have logistic growth, but now instead of k, I'm going to use L. So far, so good? Okay. Now, these are like my G and script G when we're talking about the growth functions. Now I want to talk about interaction. Okay? It's competition, which is an example of an antagonistic relationship. Neither species benefits from the presence of the other, and in fact, they are harmed by. So I'm going to be putting minuses here. Now, the species have to come in contact with one another, so we can look at all those different functional forms I listed. We're going to go with the simplest, just a mass action. That the sheer volume of animals that are in the area, that's going to drive up that interaction rate. So CXY and CXY. I've used the exact same thing there because I want the interaction to be symmetric. Okay, everybody with me so far? Okay, great. I'm going to be using red now for X species facts and blue for Y species facts. Just going to kind of help us keep things straight, okay? But step one here that we're going for is to find the fixed points, all right? That's our first goal. And it's where we're going to meet our first challenge because we are solving kind of crazy nonlinear functions simultaneously. They're quadratic functions. And so I want to make sure that we are able to keep everything straight in our heads, all right? So let's work with dx dt equals 0 first off. So dx dt equals 0. All right. And so we've got rx times 1 minus x over k minus cxy equals 0. And one fact should jump out at us right away. Both of these dudes have an x in them, so I can factor that out, which tells us that x equals 0 is one of the solutions. Now, whenever I do that, when I have, it could be this or this, I make sure to write or in giant letters so I don't miss it, okay? And now I'm going to kind of multiply things through, and what I find is that r minus r over k x minus cy equals 0. And I'm just going to rearrange this a little bit because I don't like looking at lines like that. I like looking them at y equals business. So y equals r over c minus r over ck x. Now you might be tempted to say, hey, there's a line, so I have a line of equilibrium. But we need to keep in mind here, this is just x species facts. In order for there to be an actual equilibrium for the system, both of my equations have to be equal to 0 at the same time. So this is just the line along which dx dt would equal 0. And so we have to find where that intersects the line along which dy dt would equal 0. I'll get into a little bit more of this graphical interpretation of things when we're done with all this sort of just straight up analysis and doing algebra sort of business. Okay? All right. First thing I want to do is I want to use this x equals 0 fact, and I want to plug it into my dy dt. Okay? So in order to do that, what I'm going to do, I'm actually going to use purple, because I'm going to be combining the facts here. So I'm going to get sy times 1 minus y over L minus c times 0 times y. This should equal 0. Okay, so I've combined that x fact with this whole big y fact. Okay, and I get this. Now, what's wonderful is c times 0 times y. Well, that's just 0, so that whole term vanishes. And so now I get an sy times 1 minus y over L equals 0. And so this is solved when y equals 0 or y equals L. You should notice that I don't bother to entertain the situation of when s equals 0. Because we have to remember here, parameters, while I've given them variable names here, r, k, c, s, and l, they are fixed for this problem. So they have a numerical value. And what we're left with is to find the levels of populations for which we're at balance. So we need to be always solving for x and y. Okay? This gives me 2 equilibria points already. All right? So I'm going to just kind of write them in the top here. I've got the equilibrium point 0, 0. That's using x equals 0 and y equals 0 facts. And I get the equilibrium point, whoops, my arm hit the bottom here. Stop it. 0L. Equalis the devilneck. Ooh, cussing in main Quebecois. There we go, 0L. And that's again using the x equals L and then the y, x equals 0 and the y equals L fact that resulted from that. So far, so good? Okay, great. Now, let's go ahead and cordon this stuff off. Okay, that train of thought is done, right? I took my x equals 0 from this or statement here, and I followed it to its natural ending. So now I have to consider the other part of that. The y equals r divided by c minus r divided by ck times x. I have to follow that train of thought down now. Okay? First thing I'm going to do is just a little bit of, notation here that will help me. Okay, I should notice from the dy dt equation that I can rewrite it like y times s times 1 minus y over L minus cx equals 0. All right, so I factored out the y. Now you may be tempted to say like, okay, cool, y equals 0. I want to step away from that. While you could do that, we end up getting in a circular thing where we aren't following this sort of natural top-down progression. Okay? But what this does tells me is either this is 0 or that is 0 solves this problem. Okay? Now, I need to combine that with the x fact we have right here. Right? So in order to combine those two facts, we are able to assert the following. When y equals 0, that's the equivalent of saying r divided by c minus r over ckx equals 0, because that's what y equals according to that little red star right there. Okay? And that implies, if you just do the algebra, that x equals big K. Okay? And if x equals big K, and I plug it back into that star equation there, I then get y equals r over c minus r over ck times k. Holy crap, that equals 0. So we've got our third equilibrium point here, where x equals k and y equals 0. Now, what some of you don't know is that this is my third time making this video because I keep screwing the algebra in the next part up. So don't let me, okay? What I'm going to be doing now is taking this bit of information. Okay, well, what if that whole big thing equals 0? And combining it with my red star expression. All right, let's take it slowly so I don't mess it up again. Then I have to restart the whole video. All right. I'm going to multiply everything out here. S minus S over L times Y, but I'm going to use the red star expression for Y. R over C minus R over CK times X minus CX should equal 0. What we can see here now is that we only have parameter values, S, R, C, L, and K, and X. So we can solve this for a particular value of X. Let's try to do that without screwing up this time. Then, all right. So I've got an S minus RS over CL plus RS over CKLX minus CX equals 0. Just multiplying the S over L out. I'm going to take the X terms, leave them where they are, take the other parameter terms, move them to the other side of the equation, and just solve for X. Okay, that's just what my goal is here. My eyes are going down here because that's where things are on my big screen. I'm sorry, I should look right here because that's where you are. You're special. You're the focus of this video. Thank you. Okay, so I've got, got a crick in my neck. I've got RS minus C squared KL all divided by CKL, and that is multiplied by X, is supposed to be equal to RS minus CSL divided by CL. Ooh, I didn't screw it up this time. Solve for X, okay? I get X equals. Now, I'm going to do algebra sort of on one line here, okay? So we're going to be dividing by this fraction that's in front of the X, okay? So we're going to flip and multiply. So this C cancels with that C, and this L cancels with that L, okay? This K is not found in that denominator anywhere else. Perfect. There are no shared terms on the numerator here. We've got an R and an S, and then a C squared KL. So there's going to be no cancellation possible there. And so what I'm going to wind up with here, when all is said and done, is I'm going to have a KS times R minus CL divided by, sorry about the squishiness here, I'm going to do some erasure in a second, divided by RS minus C squared KL. Now, this might not feel good for you because it's an ugly expression, but it's correct, and that's really the important part here, okay? It contains all the right information, and it's something that we can work with here, okay? So to cordon this work off here, I'm going to write that fact down right here. X equals, so we're just going to kind of rewrite it, KS times R minus CL divided by RS minus C squared KL. A nice, big, ugly-ass expression. Okay? Now, what do we have to do with that? This expression I just wrote down in black needs to be replugged into red star in order to figure out what the y is that pairs with that brings both equations to equilibrium. Oh my God, right? Take a look at it for a second, okay? Just breathe it in. Yes, it's ugly. It's not impossible, okay? And I am going to skip that level of algebraic work here and just write down what my answer is. The reason I'm going to skip it is it's that much algebraic work, and I don't feel like doing it, okay? But y is going to equal, and we're going to see some symmetries here in the two values. L R times S minus CK divided by RS minus C squared KL. So we see there, the carrying capacities are swapped, the intrinsic growth rates have swapped on the numerators, and then my denominator is exactly the same because the denominator is symmetric with respect to the properties of the two. Okay, so this is wonderful. This right here, this is the x and y component, whoops, of our fourth equilibrium point. Okay, so we have 4 equilibria. Holy smokes, a whole bunch of stuff to look at here, but we're done step 1. We found our fixed points. Okay, and I know this looks unorganized, but let's think about what I did. Okay, I took the first equation, I set it equal to 0, and I broke it up into the cases necessary. Then I took the first case and then combined that with setting the second equation equal to 0, and I saw what I concluded. That's all right here. Okay, then I took the second case, that's red star here, and I again took it through the second equation equals 0 to its natural conclusions, where I got a K0 and then this ugly one right here. So far, so good? I think so. What's our second step? We found 4 equilibria. We need to determine their stability in order to do some analysis. Now, what the stability is in our fixed point equilibrium world here is that I have to linearize my system and then evaluate that linearization at each of the equilibria to find trace determinant or the eigenvalues, whichever one's easier, to say, hey, this is what's going on. Okay, so let's do step 2, shall we? Step 2, linearization. Tap again for text bold options. I don't want to. Oh my God, go away. How do I make it go away? Oh shit. Pencil. I just cussed. Is that the first time I swore in these videos? I don't think so. Linearization. I'm so glad I wrote that out because it's definitely clear and easy to read. All right. To do linearization, the goal is we have to find our Jacobian and then evaluate it at the equilibria x star, y star. And the Jacobian matrix, if you remember, is a 2x2 matrix of the partial derivative of f with respect to x, the partial derivative of f with respect to y, the partial derivative of g with respect to x, and the partial derivative of g with respect to y, where f is the right-hand side of my dx dt equation, and g is the right-hand side of my dy dt equation. So far, so good? So simple, right? Yeah. So let's find the Jacobian matrix in general here. All right. Take a look at your notes right now so you can follow through so I don't have to flip back up to the slides, okay? The partial derivative of dx dt equation with respect to x is r minus 2r over k x minus cy. The partial derivative of f with respect to y is minus cx. Cool. Now we look at our dy dt equation. The partial derivative of that with respect to x is minus cy. Nice. The partial derivative of dy dt with respect to y is going to equal s minus 2s over l y minus cx. Close parenthesis. Make sure that's what you got. Okay. Now, this in and of itself is not what we're after. We're after this at each individual equilibrium point. Now, it looks ugly, but generally speaking, when we plug in equilibrium point information, this simplifies a lot, especially when we have equilibria that involve zeros. Okay. First equilibrium point we found was the origin. So let's evaluate this Jacobian at 0, 0. I get R, 0, 0, S. Holy smokes, that's a nice, simple matrix. Now, something that I should have said at the beginning, but I didn't, is that we're assuming that R, K, C, S, and L, hard to count to 5 that way, are all positive parameter values. Okay, so that we put minus signs and plus signs so that we know how we're using them. All right, since these are all positive, my eigenvalues in this case, lambda, is R and S. There are two real values, both of which are positive. What kind of equilibrium is the origin? You got it? It's an unstable node. Good job if you got it, okay? The next equilibrium point that we had was x equals 0 and y equaled L. So let's plug that information in here, okay? My top equation now becomes R minus CL. This one is still 0. This one is minus CL. And then this big one right here, plug in L for y. 2 times S times L divided by L is just 2S. So I've got negative S. And this is where our first problem arises, okay? My eigenvalues are negative S and R minus CL. So the negative S means that in at least one direction, I'm stable. Now, R minus CL, what does that mean? Well, it could be positive, but it could be negative. So we either are going to have a saddle if R minus CL is positive, or we have a stable node if R minus CL is negative. That makes sense to y'all? And so we have a couple cases here, and I'm writing those down as notes just to keep track of them, okay? Let's move on to the next equilibrium points that we got. I think I can stretch the page out like that. Yeah, I sure can. All right, my Jacobian at the next point was K, 0. All right, this is the last easy one. All right, we plug in X for K, 0 for Y. I get negative R. Excuse me, negative CK, 0, S minus CK. So this is a similar situation to the previous one we just did, where my eigenvalues are negative R and S minus CK, which we can see is of a very similar form to the one we had before, right? Now I take a peek at this, we have two cases. This one's always negative, so I know I'm always stable in at least one direction. So my fixed point is a saddle if S minus CK is positive, or it's a stable node if, whoops, I almost write R minus CL. If S minus CK is negative. So far, so good. These cases aren't going to make sense to us yet. They're going to make sense to us when we try to puzzle piece everything together. Okay? Now, the last one is a little something of a horror show. Let me see here. I want to make sure how I tackled it. What is this? Please hold. No idea why I wrote it like that. Okay. Let's just move forward. All right. When I plug in the fixed point here into those Jacobian terms, things are going to get messy. Okay, so I'm going to do a little bit of pre-work here to be able to plug them in without having to deal with the entire matrix all at once. Okay, so to do that pre-work, oops, not with one finger, I need two. Whoop, is I want to say, okay, let's take r minus 2r over kx minus cy. That's the first thing I'm going to work with. R minus 2r over kx minus cy. Okay, and this is where we're going to plug in, if I scroll way up here, these two bad boys in. All right, for x and y. And so we can already see how it's getting a little messy. Now, this is straightforward algebra. I didn't say it's easy. I said it's straightforward algebra. All right, so I'm not going to do it out for us here today. I encourage you to pause it. Pause the video right now. Do it on your piece of paper. And then unpause it to see if we got the same answer. Hopefully we did. And if we didn't, hopefully you're wrong. And then I'm right. All right. So pause. Okay, now that you've done all that good hard work, what you should have gotten was minus rs times r minus cl divided by qrs, which is rs minus c squared kl. That's what you should have gotten for that term. Maybe. Okay. The next term that we're working with is negative cx, evaluated at x star. Go ahead and pause it. Okay, great. Now that you've done all the hard work, I don't know why I'm quiet. It's not like you paused it and then can still hear me speaking. That wouldn't make any sense. You should have gotten negative cks times r minus cl divided by rs minus c squared kl. So far, so good? Great. The next term is negative cy. We're going to plug y star into that. Pause it. And when all is said and done, what you should have gotten was negative CLR S minus CK over RS minus C squared KL. Okay, I hope we're still matching. Okay, and then the last one that we have to do is S minus 2S over LY minus CX. And we have to plug in X star and Y star into this. Again, pause this and then come back to it. Okay, what you should have gotten was negative RS, S minus CK divided by RS minus C squared KL. All right, so these are the 4 entries into the matrix. Okay, this results in, quite frankly, an awful looking characteristic polynomial. Like if I were to write out the characteristic polynomial, okay, you'd get a lambda squared. Now let's go ahead and call this star. Let's call this cross. Let's call this apple. Come on, apple. There we go. And let's call this kitty cat. Bear with me. Okay. So I'd get lambda squared plus parentheses star plus kitty cat. Let's put a negative sign right there because that's appropriate. Lambda plus star kitty cat minus cross apple equals 0. You can already see it's going to be fairly intense to look at and to work with. Okay, I don't want to do it. You probably don't want to do it. No one wants to do it. But this is a case where trace determinant stuff will actually help out a lot. Okay, so I'm going to rewrite this essentially as a matrix. Okay, so the matrix that we are working with here, let's go and write it as A. and I'm going to leave a lot of room here. Okay, I'm going to write it as negative RS, R minus CL over SR minus C squared KL. The next term is negative CKS, R minus CL divided by SR minus C squared KL. Running out of room as per usual. Negative CLR, S minus CK divided by SR minus C squared KL. And then finally, negative RS, S minus CK, all over SR minus C squared KL. Now, this is a time where you should like make a note for yourself, like when the characteristic polynomial looks horrendous, don't find the eigenvalues. Just save yourself that trouble, okay? Let's look at the trace. The trace is this term plus this term, okay? Now, if I look at that, they both have RS in the numerator. They both have SR, I don't know why I wrote it like that, minus C squared KL in the denominator. I can factor that stuff out, all right? So my trace is going to be equivalent to the following. Negative RS divided by RS minus C squared KL. And then it's just the sum of those other two numerators. R plus S minus CL minus CK. That's my trace. All right. That seems a little bit easier to work with here. Let me go ahead and get rid of like the bottoms of those things. Okay. Okay. The next part is the determinant, which is a little bit ugly, but I'm going to compute the determinant by multiplying the diagonal elements and then subtracting from that the product of the off-diagonal elements. I'm going to write it down in a way. So multiply them, like come up with that expression of this minus this, and then factor out some uncommon stuff. Okay, because you'll notice my diagonal multiplication is going to have this times this, and my off diagonal multiplication is going to have the same thing. So we can do a little bit of factoring. All right, so pause it, then come back and see if you got the same thing. What you should get is RS squared minus RS C squared KL, okay, times R minus CL over SR minus C squared KL times S minus CK divided by SR minus C squared KL. Okay. Now this is where we need to evoke the context of the problem. The context of the problem. All right. Let's go all the way back up to this. All right. These mixed points only matter within the context of the problem if they are positive. If they're negative, well, that's fine mathematically, but we actually don't care about them mathematically. Okay? So the first point here, if I look at this x expression, okay, r minus cl, if it is negative, then rs minus c squared kl also needs to be negative. Or if it's positive, then that part also needs to be positive. And what you find is that either r minus cl is positive, s minus ck is positive, or they're both negative. Does that make sense? Take a look at that for a second, okay? If they're both positive, then their product should be positive. Let's take a peek, right? Because this doesn't really cover the denominators so much, right? Okay. If, how do I work this out here? Ouch. That hurts. If r minus cl is positive, then r divided by c is greater than l. So far, so good. By similar token, if s minus ck is positive, then s over c is greater than k. right? I just read it like this because it helps me sort of wrap my brain around this next part. This means that RS over C squared is greater than LK. Right? If I get two bigger numbers and I multiply them together, that will be bigger than the two smaller numbers multiplied together. Great. This just implies that RS is greater than C squared, let's go right at KL, which means RS minus C squared KL is positive. Cool? Now, reverse all the inequality signs. Everything still works out, right? They're both negative, yada, yada, yada. Everything works, okay? So what that's telling me here, if I look up at this whole big expression, okay, it means I have a whole bunch of cases that I need to be able to crawl through and work on, okay? This is a fact that we're going to keep, and then we'll do the reverse of it when everything is negative, and then we'll make pretty pictures, and everything will be great. Okay, so bear with me for just 1 second. I'm placing that right there. Okay, but what's important to note is the following, okay? If both of these are positive, then think about R plus S minus CL minus CK. Oh, that's just the sum of these two things. That up there would be positive, which means I'd have a positive divided by a positive, all multiplied by negative RS. Or if everything was reversed, then I'd have a negative. That denominator would be negative. And again, it doesn't change the sign of my trace. My trace is always negative in this case. So we always have either stable or a saddle, right? We're always in that situation. We can't be unstable at this point. So now we got to look at the rest of this bullshit here. Okay? Now, R minus CL, S minus CK, and SR minus C squared KL all have to have the exact same sign. You with me? Which means this whole block right here has to be positive. Okay? Okay. If I look at this right here, I can factor out an RS. And so I get RS minus C squared KL. So the entire thing here is going to be determined by that sign, which is determined by these signs. So it's either going to be positive or negative. So I'm going to have a stable node or a saddle in two different scenarios. So let's put all this freaking information together. Okay, it's a lot. So what we're going to do is we're going to draw several of these, okay? Let's draw one right now, and we will cover what case we're doing as we start to make our various assumptions, okay? So here's X, and here's Y, okay? Now, K and L are positive values, so I know I have a fixed point at 0, 0. Let's go ahead and color these, okay? Orange fixed point at 0, 0. A red fixed point at, this is 0K. A yellow fixed point, which is invisible. We're not going to use yellow. A pink fixed point. That one's visible. Okay, great. At 0L. And then we have that big ugly one. All right. We need to figure out where the hell that lives. All right. There's so much problems with this. But we know both coordinates are positive, so we know it exists in the first quadrant. Right? I'm doing this. You can't see my pen. I think I can draw a square. How do I draw a square? I thought I could draw a shape. Maybe I can't. Anyway, we know it lives. Let's go ahead and highlight it green. Okay. We know it lives somewhere around here. That's how I draw a square. Okay. I know it's in the first quadrant. I'm not entirely sure where, and it's important that we decide where it goes, or we figure out where it goes. Because, in some sense, I've got this line right here, this dashed line. Okay? It could be below or above, and each of those things, that's important stuff to make note of, right? I've got, excuse me. X equals K is my Why does it keep going to the right? X equals K is the value of X for when there's no competition. All right, so that's an important cutoff. And Y equals L is the value for Y for when there's no competition. So that's another important cutoff. So it's like, where am I in this when there's competition? Now, it should make sense that I am below where those two lines intersect. Right? It should make sense that I'm in this region here. Whoops, that fixed point is somewhere, in here. Because if it wasn't, then basically there'd be this weird thing where competition is helping them out. All right, forget it. It's just not going to let me draw that second square. All right. So we need to go through the process of saying, hey, these fixed points way up here, are you bigger than K? Are you bigger than L? What's going on? All right. We need to make that decision. And all of that is just plain horrendous work. But it's something that we have to do. And so I have this written down right here. Okay, great. Since it's competition, and I want to keep it within the context of mathematics, within the context of the biological example, all right, it needs to make good biological sense. Okay? So I need that Ks times R minus Cl divided by Rs minus C squared Kl. I think I said Rs in the top. I didn't mean to. I want this whole big thing here I want to understand its relationship to the value K. Right? So, because this is the X coordinate of my fixed point, I want to know, am I to the left or to the right? That's the first thing I need to determine. All right? So just for grins, let's subtract it and let's see what we get. All right? By combining all this stuff, I get KSR minus CSLK minus KSR plus, I ran out of room. It's the curse of working with these giant expressions. KSR minus CSKL minus KSR minus C squared K squared L, all divided by RS minus C squared KL. First thing we should notice is these two bad boys cancel each other out, leaving my numerator as negative. All right. This whole big thing right up here, this is all negative. And this thing right here is either positive or negative depending on the case that we're in, right? Joy. So its relationship is going to depend on what's going on. Now, I would like all of this to be negative. Because then if it's negative, then it makes sense that my competition is not mysteriously helping out the population. Okay? So what I need to do then is I need to make the assumption that this bottom down here, that's positive. Which brings us to exactly this case right here. That R minus CL is positive, S minus KC is positive, and RS minus C squared KL is positive. That is the case that we're in. And that's in order to put the coordinate to the left of this axis, and below this axis you make the exact same assessment here by relating the coordinate of the y to L. I know I've been talking for a long time about this. What this essentially means is that I've got a fixed point somewhere right here. Okay? Apologize this is taking so long. We need to evoke our stabilities. 0, 0 point is unstable. So that means that nearby that orange point, I'm going away from it. Okay, so I'm just going to draw a couple lines right there. All right. Now, our next point, 0L, was either a saddle if this was positive or stable node if it was negative. But we've determined that this case is bad. So we know it's a saddle. So in order to evoke that that pink dot is a saddle, then near it, I need to be attracting from below and above, and then repelling outward somewhere. Why do I know it's attracting from below? Well, if it was repelling, then the pink arrow would come in direct contact with the orange arrow, and they would smash into one another, and that can't happen, all right? So we don't want that, so I know it has to come up from there. So far, so good. By the exact same argument, I know that K, this fixed point right here, is also a saddle. Come on. That it's attracting and repelling. So you see I've drawn the little vignettes of linear analysis around each of these. Okay? The final point, when I look at this big whole ugly thing, all the work that we've done, we've got a negative trace. And now remember, this whole thing was positive, and then it all came down to the sign of this, which we've argued has to be positive. So it's not a saddle, it's a stable point, and I'm going to argue with you until my head explodes that it's a stable node, not a stable spiral. Okay? The reason I don't want it to be a stable spiral is I can't really rationalize how that would work. Okay? I can see this. Whoops. Come on, baby. There we go. Making sense to me. Okay? Using the saddleness of each of the boundary equilibria to push towards it. When I'm far away, it behaves a bit more like a node when I'm far away from those saddle points. And then the origin here is pushing outward, and it could go for a while towards one of these saddles, but then it swings up or to the right. And then it kind of folds in, and then it has something like a straight line solution that leads there. Okay? If it were a spiral, the part that I couldn't rationalize here, and I'm going to do this in brown. Okay? I want you to pay attention to this right now. We're going to erase it, but if it were a spiral, it needs to either go counterclockwise or clockwise. Period. Okay? Now, if I look at the orange and the red, all right, so my origin and the x-axis equilibrium, then I would move something like this. So therefore, I know that I would have to continue going like this. Okay? That doesn't seem to contradict coming off of the pink, but I also have orange and pink flow that wants to do this, which would mean it has to go clockwise. So I'd have flows clockwise and counterclockwise. That can't happen because they would have to eventually cross, and then we would violate existence and uniqueness of solutions. So that cannot happen. It cannot spiral inward. It has to come in this nice nodal sense. Now you could do algebra till your eyes bleed to show that the trace squared divided by 4, okay, is greater than delta. I don't want to. That sounds horrible. You shouldn't want to either. That's just abuse. Okay? Instead, you should be able to make these kinds of arguments. Okay? Let's summarize what we've done, because it's a little bit of a nightmare, and I think you all deserve a too long didn't read. Oh, by the way, I did the trace squared divided by 4 minus delta. It's not cool. Okay? So, let's revamp. Go through each step one by one without doing any of the work, but just summarizing results. Okay? Step 1. We found fixed points. We found 0, 0, K0, 0L, and then I'm just going to write X star, Y star. Okay. Step 2, stability. We found that 0, 0 is an unstable node. We found that K0 was either a saddle or stable. We found that 0L was a saddle or stable. And then through a bit of work, we were able to conclude that X star Y star was stable. That's it. All right. In order to get here, we're going to have the red biological relevance. This could have been a saddle if it wasn't biologically relevant. Each of those stable conditions ended up being biologically irrelevant to us. So we got an unstable node, 2 saddles, and a stable point. We weren't sure if it was a node or a spiral. Okay. Step 3, we made our sketch. Okay. We had a fixed point here, a fixed point here, and a fixed point here. And then we found that the other fixed point was somewhere around here. Okay, just what was important was that it was less than the 2. Okay. Since this was an unstable node, we drew this. Since these guys were saddles, we drew it like this. And then we concluded not a spiral by doing the following. Okay. By noting that this would have to go this way, but this one would have to spiral that way. And you cannot reconcile those two things. Okay. So all my flow ended up looking like this. And I think that really covers it. Okay. Complicated? Sure. Impossible? No, not really. A lot of algebraic work and a lot of argument to go on. I mean, this is more or less all of it. There's a bit more, but I did it on 3 pieces of paper where I wrote very spaced out. Okay. I hope this makes sense to you guys. Okay. Do I have another video? Or was this it for now? Okay, I do. I have another video of a easier example with just variables. And then I have an epidemiological example. Bye. I'm tired. Oops, I didn't push stop.